Welcome back as we move along through acids and bases. In this lecture, we're going to discuss strong and weak acids and strong and weak bases. In your textbook, it's pages 218 to 226. By the end of this lecture, you'll be able to identify the empirical differences between strong and weak acids. You'll be able to identify the empirical differences between strong and weak bases. You'll be able to describe strong acids and bases and weak acids and bases using ionization theory. And you'll be able to describe monoprotic, polyprotic, and amphiprotic acids and bases. Okay, so something to consider. Two acidic solutions. If we test one, or both of them, so 100 mils of 1.1 mole per liter aqueous hydrochloric acid and 100 mils of 0.1 mole per liter nitric acid. So what we have here are two acids. They have the same concentration and the same volume. Now when we test their pH with, say, a pH paper or a pH meter, both these solutions have a pH of 1, and this seems to intuitively make sense. They're both acids, they both have the same concentration, so they both produce the same number of hydronium ions. So they both produce same number of H3O plus ions. And we said in our last lecture that this is how we're going to judge acids now. Acids are compounds that produce hydronium when they're dissolved in water. So this makes sense. They both form the same number of hydronium ions. But here we have two solutions. Now they both have the same volume and the same concentration as the two acids on the last slide. So same volume, same concentration. They're both acids. One's hydrofluoric acid, the other's acetic acid. However, if you look at their pHs are actually not 1, which is not what we would expect. Hydrofluoric acid would have a pH of 2.1. One has a concentration of 0.1 mole per liter, and acetic acid has a pH of 2.98. So, another neat thing about these is they're actually weak electrical conductors instead of strong electrical conductors. So, they both have the same molar concentrations but higher pH. Higher pH actually means, just as a reminder, they are both less acidic. As we get closer to a pH of 7, the less acidic things become. So both of these are less acidic than our previous two solutions, and the acetic acid is actually less acidic than the hydrofluoric acid. So what this means is they're less acidic, which means fewer H3O plus in solution. So, some acids are weaker than other acids, even when they have the same concentration. So, the question is why? And the answer is some acids dissociate more than others. So, weak acids don't dissociate as much as strong acids. So, they don't dissociate to the same extent. This means the pH of one acid will differ from another of the same concentration, depending on how much dissociation happens. Their conductivity will also differ. Compounds that dissociate 100% in water are going to have high conductivity. They're going to conduct electricity easily. The compounds that don't dissociate in water or only dissociate a little bit won't conduct electricity as well. So, for strong and weak acids, here's how we're going to start writing things down. If you have a strong acid, it dissociates 100%. So we have a one-way arrow because all of it, or every single one of these nitric acids, dissociates when it gets put in water. So every single one of those molecules reacts with a water molecule to produce our hydronium ions. There's our hydronium ions. For weak acids, we have this two-headed arrow in your textbook, and the way you should write it is actually like this. I just don't have that symbol available to me on my computer, but this symbol here represents an equilibrium reaction, or one that doesn't go 100%. What it means is only some of these HFs react with water. Most of them don't. If they don't react with water, then you don't get as much hydronium ions. And so you'd have a higher pH. The solution would be less acidic, even if they have the same molar concentration in terms of the acid formula. So for a strong acid, here's the idea. We have a solution of hydrochloric acid, right here, hydrochloric acid. When you put it in water, so when you add it to water, none of those molecules stay as hydrochloric acid. Every single molecule of HCl breaks apart to form hydronium and chloride. So 100% of them dissociate. If we take a look at a weak acid, so for a weak acid, most of those molecules do not dissociate. So here we have acetic acid. It's a weaker acid. It reacts with water, and here's the reaction down here. It reacts with water to form hydronium and the acetate ion. But if we take a look at the percentage, only about 1% actually dissociate. When we put it in water, 99% of the molecules stay as acetic acid molecules, or ethanoic acid molecules. So, our concentration of hydronium is only about 1% of our concentration of acetic acid, which means our pH is going to be much higher. So in terms of memorizing, these are the strong acids. This page reference is for the 2003 data booklet. And they're the top acids on your table. In the 2008 data booklet, they're on page 8. So page 8 in the 2008 data booklet. They're separated by the from the weak acids by a gray line. So the gray line has a hydronium ion. Everything underneath that gray line with a hydronium ion is a weak acid. So oxalic acid, sulfurous acid. Some of the acid names are different depending on the book that you're using. In your 2003 data booklet, they have hydrofluoric acid, and they don't have that in the new data booklet. But the data booklet gives you a list of acids. The ones above the gray line are strong. The ones below that hydronium ion, the gray line, are weak. So, because we can have strong and weak acids, we can also have strong and weak bases. So it's the same idea. For those bases that have hydroxide ions, all of them dissociate 100%. So all bases with OH in their formula are considered strong bases. The weak bases are the bases that react with water to form hydroxide. So for example, NH3 would be a weak base because it has to react with water to form hydroxide, and not every single one of those molecules is going to react. Most of them stay as ammonia. So for the strong bases, here's some common strong bases. Notice that they're all hydroxide bases. They all have an OH in their formula, and so any hydroxide that we can, so these are just examples, but any, or better yet, here it is here, all hydroxides are strong bases. If it has a hydroxide in the formula, it's a strong base. For weak bases, in terms of a reaction, here's how we're going to write them. Here's an ammonia molecule. We have to make it react with water to get those hydroxides. Because ammonia is polar and because water is polar, ammonia strips one of those hydrogens off of water. So there used to be a hydrogen here on water. It got stripped off. We'll say it's this one, leaving an OH left for our water molecule. Very, very few of these actually react. only about 1% of the ammonia molecules in solution react with water to produce a hydroxide. So in a 0.1 mole liter solution of ammonia, only 1% of them, or only about a 0.001 mole per liter of hydroxide will exist in that solution. So that was strong acids and strong bases, and weak acids and weak bases. Now we're going to look at some more terms, monoprotic and polyprotic. So for monoprotic, if we just take a look at the word, mono means one, and poly means many. So emprotic, these are protons, which is another word for our hydrogen ion. Hydrogen ions are protons. So we're talking about acids that have one proton or one hydrogen versus acids that have many hydrogens. There we go. So monoprotic acids react with water on a 1-to-1 ratio. Another way to say that, or to show that, is for every 1 molecule of HCl, we get 1 molecule of hydronium. So it takes 1 water to react with the HCl, we get 1 hydronium. For polyprotic acids, they can react with more than 1 water molecule. And an example would be sulfuric acid. Sulfuric acid has 2 hydrogens in its formula, so it can react once with water. When it reacts with 1 water molecule, it would lose 1 hydrogen. So there were 2, now there's 1. Notice that we now have a negative ion, because when we lose our hydrogen, it's an ion, so we lose a positive charge as well. What started as a compound with a 0 charge becomes a compound with a -1 charge, because we lose 1 positive charge from that compound. But notice that our product here, this HSO4, the sulfate ion, has a hydrogen still. So this molecule has the potential to react with water again, so we can write it in a second reaction. So here's our sulfate ion. It reacts with water again, it becomes sulfate. So the hydrogen sulfate becomes sulfate. Notice again that our charge dropped. When we lose that hydrogen, we lose a positive charge with it because it's a hydrogen ion, so our -1 becomes a -2. And so this compound, or our sulfuric acid, can actually produce more than 1 hydronium ion per sulfuric acid molecule. Note that the second reaction is minimal, or it's less. Not every single one. See this 2-headed arrow? Not every single one of those hydrogen sulfate ions will react with water to produce a hydronium ion. So it's not quite a 2-to-1 ratio. It's somewhere in between. So here's an example of what we're talking about. If we take a look at something like phosphoric acid is H3O+, or H3, I don't even know what I just said there. H3PO4 is phosphoric acid. So it's going to react with water. When it does, it loses 1 hydrogen ion. So it becomes H2, there's a loss of 1, PO4, negative, because when it loses that hydrogen, it loses a positive charge. It's a hydrogen ion. From that, we're going to get a hydronium ion. But notice that our product still has more hydrogen, so we can react it again. So our product becomes the next reactant in another reaction. And so we have, again, this dihydrogen phosphate ion can lose 1 hydrogen. So it can become HPO4, and again, its charge drops by 1. So it used to be -1, now it's a 2 negative. It's also aqueous, and we get another hydronium ion. And if we take a look, our product still has 1 more hydrogen, so it can undergo another reaction. Our HPO4 2 negative, or our hydrogen phosphate ion, becomes just a phosphate ion. So it becomes PO4 3 negative. Again, it loses that positive charge, so what was once a 2 negative becomes a 3 negative, and we get another hydronium ion. And so phosphoric acid can react with up to, or each molecule of phosphoric acid can react with up to 3 water molecules. So, and not everyone will. Notice that for each of these reactions we have a two-headed arrow, which means none of them are 100%. None of them have all of the acid reacting with water molecules. Each one only has a few. And each reaction gets progressively less and less likely to happen. So the H3PO4 reaction, if I can just find my pen tip here, this reaction is going to happen to a greater extent than the next one. A lesser extent, and this reaction is, I guess for lack of a better word, the least likely to happen, or the one that happens the least often. In order for each progressive reaction to happen, we have to have some of the reactant present. In other words, in order for this H2PO4 to react, some of it had to be produced in the first place from our initial reaction. And look at that, I just had it written down twice. So phosphoric acid reacts with up to 3, I guess if you want to fill in the blank there, 3 water molecules. So, monoprotic versus polyprotic bases, same sort of idea, except it's reversed. For our bases, monoprotic bases react with water on a 1-to-1 ratio. So they produce hydroxide in a 1-to-1 ratio. So for example, KOH, for every 1 KOH we get 1 hydroxide. Polyprotic bases can react with more than 1 water molecule. In this example, dinitrogen tetrahydride reacts with water. When it reacts once, it produces an ion and 1 hydroxide. And it turns out that for this particular example, now this isn't one that I would expect you to know or even be able to predict, but because this has 2 nitrogens, if we just drew its Lewis structure, and right now it has 5 hydrogens, so there's 4, there's 1 hydrogen here. Now, because nitrogen is very polar, this nitrogen here is a little bit negative, right? It's stealing electrons from those 2 hydrogens, it's hogging them a little bit, which means there's actually another spot for a hydrogen to hop onto. And so, to a lesser extent, we can react our N2H5 with another water molecule, and when we do, we get N2H6. Notice the charge goes up by 1 on our anion, and we end up with or our cation, sorry, and we end up with another hydroxide. So we get 2 hydroxides. So it's a greater than 1-to-1 ratio. Notice the second reaction is less complete than the first. So it wouldn't be quite a 2-to-1 ratio because not every single one of those N2H5 pluses is going to react with water. So a polyprotic base can react with more than 1 water molecule. And so sodium carbonate is a diprotic base. We're going to write reactions that can occur when it dissolves in water. So because it's a base, because they told us it was a base, we know it has to produce OH negative. It has to because it's a base. And so we'll start with our formula. Sodium carbonate is Na2CO3. And we're going to react it with water. So we're going to react it with a water molecule. And we know it has to produce a base. So what that means is, well, hold on, we're going to start this again. Okay, so let's take a look at an example here. Sodium carbonate is a diprotic base. We're going to write the reactions that occur when sodium carbonate dissolves in water. So the first thing we have to do is decide what's going to happen to our sodium carbonate. So NaCO3, there's actually two of them, 2 NaCO3 solid. When it gets placed in water, we can check our solubility table, and what we're going to see is it dissociates into sodium ions and carbonate ions. And so when we put it in water, we actually end up with sodium ions, carbonate ions. Now we've got to decide which one of these things can make OH. We know we have to make hydroxide ions by stealing H pluses from H2O. By definition, that's what a base does. And because they're telling us it's a base, that's what we're going to try and do. So when we take a look at these two ions, we're going to say which one's the most likely to attract positively charged things, or positively charged hydrogens. And if we take a look, sodium, it's already positive, so it's not going to attract other positive things to it, right? Things with the same charge repel each other, so sodium isn't going to attract hydrogens. But if we take a look at carbonate, and I made a little mistake here, this is actually 2 negative, this carbonate ion it's negatively charged, so it can attract positive things. So that's what we're going to react with water. So here we have our CO3, 2 negative, and it's aqueous. When it goes into water, so we write it as a reaction because we're looking to make a base, and because it's not a hydroxide base, we know it's going to be less than 100%. So we can use a two-headed arrow. Now when we do this, it's going to steal one hydrogen from the water. So our CO3 2 negative is going to gain an H. It becomes HCO3, and now the charge becomes -1 because it gained a positive charge. It stole a hydrogen from the water, a hydrogen ion, so the water becomes hydroxide. And if we take a look, bicarbonate has the potential to take another hydrogen. If we see this negative charge here, since it's negatively charged, it means that it can accept another proton or another hydrogen ion. So HCO3 negative can react with water again. So we end up with H2CO3 aqueous. So our bicarbonate ion gains a hydrogen ion, so it goes from a negative charge to no charge because it gains 1 plus. And our water lost a hydrogen, so it becomes hydroxide. So those are the two reactions that can happen when bicarbonate is placed in water. So each bicarbonate, or each carbonate ion, can react with up to 2 water molecules. Okay, sulfur dioxide is a diprotic acid. Write the reactions that occur when sulfur dioxide is dissolved in water. So first we need the formula for sulfur dioxide, SO2, and it's a gas. So because this acid is a weak acid, we need to figure out what the acid actually looks like. So when it gets put into water, because it's one of those organic acids, those non-metal oxides, when it gets put into water, it's going to go and form H2SO3. And so we need to do that step first in order to get something that's going to donate hydrogens to water molecules. So we shove all of our molecules together, or shove our two molecules together into a compound, and now that compound can react in water. So H2SO3 can now donate a hydrogen ion to a water molecule. Now we end up with HSO3 negative. It lost one positive charge, so it becomes a negatively charged ion, and that positive charge goes on to the hydronium. So, and then we take a look at our products and we say, well, this product here could react with another water molecule. So we end up with, and because it's a weak acid, we want equilibrium arrows or that two-headed arrow, showing us that the reaction doesn't go 100% to the product. So not every single one of our hydrogen sulfite, or our sulfurous acid, or sulfurous acid, not every single sulfurous acid molecule reacts with water. And now we have a product that can also react with water, HSO3 negative. It can react with a water molecule because it has a hydrogen there. And it becomes SO3 2 negative. It loses that positive charge again when it loses its hydrogen, and it can form another hydronium ion. So, in order to get these reactions, or I guess get the question right, the first thing we're going to do is, the first question you want to ask yourself when you see one of these compounds is, what happens when it dissolves? In the last question, so let's go back a slide here. In this slide, if you take a look, we did the same thing, and we said, what happens when this dissolves? So, the things that we noticed is it's a ionic compound. So check solubility table. So when we see an ionic compound, we want to know, is that ionic compound going to dissolve? If it doesn't dissolve, if it doesn't ionize, then we're done, because it can't form any acid molecules if it can't at least dissolve in the water. So we did that first, and then we said, well, now that it's dissolved in the water, how can it react as a base? So because the question asked us to react it as a base, that's how we approached it. For this question, when we take a look at SO2, we say, well, SO2, that's not ionic, that's a molecular compound, so we can't use our solubility table, but we can use our new definition, our modified Arrhenius definition for acids. And using that definition, we can say, well, when this goes into water, it forms an acid compound. And now that we have the acid compound, we can make it form hydronium ions. Again, we approached the question as an acid because it asked us to. And so for these questions, you won't be asked necessarily, well, the sulfur dioxide you should know is an acid from the last lecture, but for ones that you haven't done before, you won't be assumed to predict if it's an acid or a base necessarily. You'll be told this acts as an acid, show how it acts as an acid. And so there aren't many examples in the book, but take a look at those, and I will see you in the next